In our next discussion, we are going to discuss oxides of transition metal. Oxides of transition metal means oxygen combined with transition elements. So it can be in any number, any stoichiometry ratio. That's why MXOY. X is number of metal atom, Y is number of oxygen. In that, what specifically we are going to discuss is that metal oxide can be acidic, it can be neutral, or it can be basic. In lab, while you are in lab, in case you are provided with metal oxide and you are asked to identify metal oxide is acidic or basic or neutral, what we used to do, just dissolve the metal oxide in water, metal oxide in water, metal oxide in water. So initially the metal oxide and we have water and we will obtain a solution. Once we dissolve metal oxide in water, we obtain a solution. Now check the solution with both the red litmus and blue litmus. Both red and blue litmus. Now this is A, B, C. We obtain metal oxide. On metal oxide in water, we obtained a solution A. We are testing with red litmus. If red changes to blue, and we are checking with blue litmus, there is no variation. No variation. In solution B, red also no variation, blue also no variation. Red remains red, blue remains blue. In solution C, red remains red, there is no change, but blue changes to red. If the red changes to blue, so it indicates the solution is basic. Solution is basic. No change in color, no change in both the litmus, it indicates the solution is neutral. If the solution changes to red, the solution is acidic. If the blue litmus changes to red, the solution is acidic. So in first case, the solution become basic. In second case, the solution become neutral. In third case, the solution become acidic. What is the inference? What is this observation? What is the inferences? In first case, metal oxide is acidic in nature. MXOY, it is acidic in nature. In second case, it is neutral. In third case, it produces acidic solution, so it should be basic in nature. This is in if you are in lab, we can do this. With the only formula, how can say whether it is acidic or basic or neutral? For this also, oxidation state plays an important role. Lower oxidation state. Classify the oxidation state into three types: +1, +2, +3, +4, +5, +6, +7. This lower oxidation state, whenever metal exhibit lower oxidation state, their metal oxides are basic in nature. If metal exhibit +4 oxidation state, a compound in which metal exhibit +4 oxidation state, there the metal oxide is amphoteric. That neutral is otherwise known as amphoteric. It can, basic means it will react with only acid. If metal exhibit +5, +6, +7, it is acidic in nature. Metal oxides are acidic in nature. Acidic means it will react with only base. Base will react with only acid. Acid reacts with only base. Amphoteric means it reacts with both acid and base. Reacts with both acid and base, which means it has both the property, dual nature. Reacts with both acid and base. Those are amphoteric. In that, particularly what we need to know is +4 is general, but chromium +3 it is amphoteric. Vanadium +5 is amphoteric. Zinc +2 is amphoteric. Chromium +3 Cr2O3. Vanadium +5 V2O5. Zinc +2 ZnO. These are chromium trioxide, vanadium pentoxide, zinc oxide. These are amphoteric oxides, which means they can react with both acid and base. Very important one. Okay. And next variation, acidic nature of metal oxide is directly proportional to electronegativity. If electronegativity increases, acidic nature also increases. So in periodic table, top to bottom, in D block series, electronegativity increases. So acidic nature, copper, silver and gold belongs to same group. Copper, silver, gold. So gold will have higher electronegativity. So gold Au2O will be more acidic than Ag2O. Ag2O will be more acidic than Cu2O. Is it clear? So this is about oxides of transition metal. Transition element. Our next discussion is about magnetic properties. Very important one. Magnetic properties. How the substances react with the magnet. See, you have metal ion plus metal ion, and you are bringing the metal ion near to the magnet. If it is get repelled, there it exhibit one type of magnetic property. If it is get attracted, there it exhibit one type of magnetic property. If it is get attracted strongly, there it exhibit one type of property. So any substance, if there is no unpaired electron, it will get repelled by the magnet. Will be called as diamagnetic. One or more unpaired electron, depend on the case, one or more unpaired electron, it will attracted by the magnet, but the attractive force which is existing between the substance and the magnet is very small, so weakly attracted by the magnet. The substance which are weakly attracted by the magnet will be called as paramagnetic. If the substance has two or more unpaired electrons, it will be strongly attracted by the magnet. Those substances will be called as ferromagnetic. These are three major types, and we are going to discuss only these two. This is not in our syllabus. Along with this, there are some other magnetic properties, that is ferrimagnetic, anti-ferro, anti-ferri, n number of types of that. These are all temperature based magnetic property. On decrease in temperature, on increase in temperature, it will vary. But there are n number of types. We are going to focus only this two, dia and para. And the quantity used to quantify means we are going to measure magnetic nature of substances, magnetic moment, represented by symbol mu. So if mu is 0, it indicates there is no magnetic moment. No magnetic moment means there are no unpaired electron. No unpaired electron is diamagnetic. No unpaired electron. If magnetic moment is not equal to 0, unpaired electron is there. It is paramagnetic. Here there is no unpaired electron. And magnetic moment of any substance is a sum of, actually magnetic moment is a vector property. It is a sum of orbital magnetic moment and spin magnetic moment. There are two types of magnetic moment. In which shell it is revolving, that will cause one magnetic moment. That is orbital magnetic moment. And whether it is upward spin or downward spin, that will cause one magnetic moment. So it is spin magnetic moment. Two magnetic moments are there. If the orbitals are close to the nucleus, their orbital contribution will be quenched. Quenched means it will get shut down. It won't be more pronounced, because orbitals, if the orbital is close to the nucleus, if the orbital is close to the nucleus won't allow the orbital to move freely or to exhibit random motion. That in that case, the orbitals have to be sit in the particular place. Orbitals have to be freezed. It can't move. So orbital magnetic moment get quenched when the orbital is close to the nucleus. If the orbital is far away from the nucleus, it can exhibit random motion. There the contribution, their predominancy, their effect will be more. If the orbital is close to the nucleus, their effect will be less. So mu orbital plus mu spin. But for 3D element, and you compare 3D and 4D, 3D is close to the nucleus. So the mu orbital is quenched, or the effect is less. If the effect is less, mu total will be approximately equal to mu spin, because it is negligible. Mu total is equal to mu orbital plus mu spin. As this quantity is negligible, we can equate mu total directly with mu spin. For 4D and 5D, it is pronounced, the effect is large. So for 4D and 5D, we need to account all the things. Clear? Diamagnetic, paramagnetic, ferromagnetic. First understand this, then understand the magnetic moment, how the magnetic moment varies for unpaired electron presence or unpaired electron absence. Then this thing, okay? What is the importance of orbital magnetic moment? In which case it is predominant. Next, we are going to discuss what is the formula to calculate the spin magnetic moment is square root of n into n plus 2 Bohr magneton. This is nothing but Bohr magneton. Capital B, capital M, Bohr magneton. Bohr magneton. Unit of spin magnetic moment. This n represents number of unpaired electrons. So chromium 2 plus. Chromium 2 plus means configuration is 3d4. 3d4, how many unpaired electron? 4 unpaired electron. So square root of 4 into 4 plus 2. You will get, this will be 6, 24, 4.8 Bohr magneton. See, how many unpaired electron? That unpaired electron point, place the number greater than 5. Any number, 5, 6, 7, any number, 4.8 Bohr magneton. You complete for this 2. Okay, calculate the number of unpaired electron correctly. Nickel 2 plus means 3d8 configuration. 3d8 configuration, how many unpaired electron? 3d8 configuration, how many unpaired electron? 1, 2, 3, 4, 5, 6, 7, 8. So 2 unpaired electron. N value will be 2. By using 2, you have to calculate the spin magnetic moment. Then for here, use the idea, then calculate. Okay. Pause the video and complete this. Okay, next. Compounds containing D block elements, the D block metals, are generally colored. Some compound exhibits very light color. Some compound exhibits intense color. In coordination compounds itself, we have discussed the reason for color. Crystal field theory gave explanation, proper explanation. Now, What is the reason for a color? Why D block element exhibits different colors? First thing is DD transition. Electron moves from one d orbital to another d orbital. Electron excites from lower energy d orbital to higher energy d orbital. Because of that, it is that is known as DD transition. As DD transitions are forbidden transition, as DD transitions are forbidden transition. Forbidden is not completely allowed. Forbidden transition. The intensity of the color is low, that is, the color is pale color or light color. As the transition is happening between same d orbital, the intensity is low. One more reason for the color is charge transfer. Charge transfer. If color is due to charge transfer, their color will be intense. Because this charge transfer transitions are allowed transition, they are not forbidden, they are allowed transition, so the color will be intense. If metal exhibit particular configuration, D configuration, D0 or D10, D0 or D10. In D10 there will be no DD transition because all the d orbitals are filled, completely filled. In D0 there is no d electron. So in D0 and D10 it will be colorless because of there is no DD transition. There is no DD. I am not saying the compounds are colorless. It will not get color due to DD transition. If it is colored means that charge transfer will happen. Keep this thing point. Keep this very clearly. D0 or D10 will not get color due to DD transition. It doesn't mean the compounds are colorless. They may be colored. The reason is charge transfer. In which case D0 D10. Though there is another configuration, partially filled configuration. In that also it exhibits pale and intense color. That charge transfer will be there. So only DD transition will give only pale color. DD transition alone will give pale color. Now try to write the configuration for this thing. Titanium 4 plus. Titanium 4 plus means first we should understand, we should know what is the configuration of titanium 22 neutral. 3d2 4s2. 4 plus means it loses 4 electron. 3d2 4s2. So in valence shell it has 4 electron, it loses all the 4 electron. Now configuration d0. Copper plus 1. Copper is d9 s1. So sorry, d10 s1. So once it loses to 1 electron, the configuration will be d10, 3d10. Here also in neutral state 3d10 4s2. In Zn2 plus it loses 2 electrons, so configuration will be 3d10. So it completely filled, no electron in d orbital. There will be no DD transition because of there is no d electron. There will be no DD transition because d orbital is completely filled in Cu plus 1 and Zn2 plus cuprous and zinc. And note down the colors of some D block element, 3D series element, titanium 3 plus purple, just for our understanding. Vanadium 3 plus green, vanadium 4 plus blue, manganese 2 plus light pink, manganese nickel 2 plus green, copper 2 plus blue. Copper 2 plus is colored because that D9 configuration. Okay. And next discussion is about interstitial compound. What is meant by interstitial compound? D block elements are metals. Metal exists in solid state. Which indicates that the atoms are arranged in a fixed position, which will lead to the formation of crystal lattice. In case, for example, if this is on arrangement, corner, edge, corner, this and all, This is not intersecting point. All the intersecting points are occupied by metal atom or metal ion. It depends on the case. If it is charged metal ion, if it is neutral metal atom. So now see, this is this is not space. In between metal atom there is space. The spaces are called voids. Any small atom, any small atom can occupy this voids. Any small atom can occupy this voids, which is existing in the metal atom. The small atom occupies the void which is existing in the metal atom, and it rise to the formation of interstitial compound. Why particularly called as interstitial compound means interstitial means the position between the atom, interstitial position. The small atom occupies the interstitial position. That's why it is called as interstitial compound. The interstitial compound is nothing but we have a metal atom, we have solid metal. In solid metal, the atoms are arranged in a fixed manner. In the fixed manner, there will be some space. The space will be occupied by the small atom, which leads to the formation of interstitial compound. Why it is important means it exhibits a property, it gives a useful property compared to the pure. It gives a property which is very useful than pure metal. Once it forms interstitial compounds, there the level of usage is very high compared to the pure metal. So the general characteristics are interstitial compounds are non-stoichiometry. Non-stoichiometry means it should not be a fixed one. It depends on the case. Non-stoichiometry. Interstitial compounds are non-stoichiometry. Example: vanadium. Vanadium hydrogen 0.6, which means for each vanadium there will be 0.6 number of hydrogen atom. We can see 6 hydrogen atom, one hydrogen atom connects 6 vanadium. In vanadium for each vanadium there will be 0.6 number of hydrogen atom. Another example is titanium hydrogen 1.7. Another example is iron 0.95 oxygen. So these are all. See, there is no fixed number. In case if you are writing zinc oxide means we will write ZnO. This is not interstitial compound because it is fixed one. Zinc exhibit +2 oxidation state, oxygen exhibit -2. It cancels and forms ZnO. But here it forms a decimal number, so it is called as non-stoichiometry. And the bonding between the atom is neither ionic nor covalent. The bonding between the small atom and metal is neither ionic nor covalent. It just occupies the space. And interstitial compounds have high melting point than the pure metal. And interstitial compounds are chemically inert. Interstitial compounds retain metallic conductivity. Interstitial compounds are odd. They are not easy to break. These are all properties of interstitial compounds. Next, alloy formation. So one more important thing which we should discuss in the block. A homogeneous solution of homogeneous solution of solid substances in which one of the component is metal, in which one of the component homogeneous solution of and write definition like this: homogeneous solution of two or more metals. Homogeneous solution of two or more metals forms alloys. Homogeneous solution of two or more metals forms alloys. And alloys can be classified into two types. One is ferrous alloy. Another one is non-ferrous alloys. The alloys which contains iron as one of the component, they are ferrous alloy. The alloys which do not have the iron as one component, that will be called as non-ferrous alloy. So the steel, cast iron, these are all example of ferrous alloy. Brass, bronze, these are all example of non-ferrous alloy. Brass and bronze both contains copper. Brass is a mixture of copper and zinc. Bronze is a mixture of copper and tin. So these are different. Okay. Brands bonds discuss, no? Brass, copper and zinc, bronze, copper and tin, solder, lead and tin, German silver, nickel plus copper plus zinc. German silver, nickel, copper, zinc, gunmetal, copper, tin, zinc. These are the different component present in the different metal present in the particular alloy. Okay. So with this we have completed the properties. Next thing, important thing, we are going to study the preparation and the properties of potassium dichromate K2Cr2O7. Okay. Potassium dichromate, name K2Cr2O7. Actually, it is a coordination compound. Chromium acts as intermediate atom, potassium acts as counter ion, oxygen acts as ligand. Now, it is a reddish orange crystal. Reddish orange crystal. It is solid. It is soluble in water. Once it dissolves potassium dichromate in water, it will produce 2K plus Cr2O7 2 minus potassium ion dichromate ion. Structure of potassium dichromate. For dichromate only we have to draw the structure. One, two, three, four, 5, 6, 7. In potassium dichromate, to calculate the charge of chromium, total charge is 0. Why total charge is 0? Because the compound is neutral and we have 2 potassium, 2 chromium, 7 oxygen equal to 0. Potassium will exhibit plus 1 oxygen state, so 2 into plus 1 plus 2 into x plus 7 into minus 2 to 0. plus 2 plus 2x minus 14 equal to 0, 2x equal to plus 12, x equal to plus 6, which means each chromium exhibit plus 6 oxidation state. Now see here, 1, 2, 3, 4, 5, 6, 6 bonds surrounded by chromium, and all 6 bonds are with the oxygen. As oxygen is more electronegative, chromium will get positive charge, and this is surrounded by 6 bonds. Here also 6 bonds. But what is the data, what is the information we are going to give from the data structure is, we have 2 CRO single bonds, 2 CRO single bonds, 1, 2, 3, 6 CRO double bonds. Two types of bond length are there. 2 CRO single bonds are there. 6 CRO double bond, which means their bond length are same. 6 CRO having same bond length. And here the bond length is 168 picometer. Here the bond length is 178 picometer. If chromium exhibit plus 2 oxidation state, if chromium exhibit plus this oxidation state, chromium configuration 3d5 4s1, chromium plus 6 means it loses all the 6 electrons from the valence shell. So here configuration is 3d0. 3d0 means it should be colorless, but it is bright reddish orange color. The reason is d6, d0, that should be it should be colorless, but it is exhibit reddish orange. The reason is charge transfer. Charge transfer from oxygen to chromium. That's why it is exhibiting color. Charge transfer happening between oxygen to chromium. Next we are going to see the preparation. This preparation part is that they can ask the question how to prepare the potassium dichromate and all. Very important one, very easy one, obviously. So with this we will complete the discussion. First we have to decide the ore for chromium potassium dichromate preparation is chromite. Chromite is nothing but FeOCr2O3, that is chromite. FeOCr2O3. First thing, chromite ore FeOCr2O3 should be treated with sodium carbonate Na2CO3 in presence of oxygen gas. It will lead to the formation of Na2CrO4, sodium chromate, and Fe2O3, iron oxide, and carbon dioxide. To balance this, if you follow the normal method, you will get the answers. But as of now, it is very important. Try to memorize the values. 4 chromite ore, 4 Fe2Cr2O3, 8 sodium carbonate, 7 oxygen molecules. So 4, 8, 7. Here 8, 2, 8. 4, 8, 7, 8 to 8. This is unknown sodium chromite ion oxide. Here this carbon dioxide is gas. Once it forms, it will escape from the reaction. Now these two are solid. This two will be obtained in the solid state. How will you differentiate this? First, how will you identify which one is sodium chromite, which one is iron oxide? Now, this should be treated with water. Once it is treated with water, sodium chromite is soluble in water. This is soluble in water. Whereas Fe2O3 is insoluble. So once we dissolve in water, sodium chromite alone get dissolved. Fe2O3 remains insoluble. So Now we have a solution which contains sodium chromate in dissolved form, sodium chromate aqueous form, sodium chromate aqueous form plus Fe2O3 solid, right? Once you filter, you will get the only sodium chromate solution. Now the sodium chromate Na2CrO4 should be treated with sulfuric acid. First thing, sodium carbonate. Second, sodium chromate should be treated with sulfuric acid. It will lead to the formation of Na2Cr2O7. Na2Cr2O7 plus Na2SO4, sodium sulfate. Na2Cr2O7 plus sodium sulfate. What is happening here? Here chromium exhibit plus 6 plus 6 in acidic medium, chromium will converted to dichromate. This is what happening. Now, this both are soluble in water. Both are soluble in water, but the extent of solubility is not same. The extent of solubility is high for sodium sulfate, so it will get dissolved completely, whereas sodium chromate, the Na2Cr2 sodium dichromate, is not get dissolved completely. And once you decrease the temperature, sodium dichromate crystallizes first because it doesn't favor the solubility process. On decreasing the temperature, sodium dichromate crystallizes first. So with the sodium dichromate should be treated with potassium chloride. It leads to the formation of K2Cr2O7, potassium dichromate and 2 moles of sodium chloride. Finally, we obtained potassium dichromate, and this is used in volumetric estimation. A good strong oxidizing agent, so it is used in volumetric estimation. It can act as oxidizing agent in acidic medium, can act as oxidizing agent in basic medium, it can act as oxidizing agent in neutral. So in all the three cases, potassium dichromate can act as oxidizing agent. Now here one question will come. Why not sodium dichromate should be used instead of potassium dichromate? The reason is sodium dichromate is hygroscopic in nature. Hygroscopic, which means it can absorb the moisture easily. If it happens, the weight will not be constant, or you can say the concentration will not be constant. It continuously changes. To avoid this only, we are using potassium dichromate. It is not a hygroscopic one, And potassium dichromate should not used in presence of hydrochloric acid. The reason is here it will oxidize chlorine -1 to chloride to chlorine. Actually, this HCl should produce a medium, but here it acts as a reactant, and potassium dichromate will oxidize the chloride to chlorine. Actually, it should oxidize some other things. In case if you are using sulfuric acid, there it won't oxidize sulfate to sulfur, but here it is oxidizing chloride to chlorine. So potassium dichromate should not use in presence of hydrochloric acid. And with this, we are completing the major parts in D block. Only one thing important remaining thing is potassium permanganate and F block. In F block, lateral contraction, that we will see later. Thank you.